Hi, my name is Max Chickering, and I'm going to talk about my paper, Statistically Efficient Greedy Equivalence Search. Greedy Equivalence Search and the statistically efficient variant of it are both structure search algorithms. And the name of the game here is that you have an observed set of data that's sampled IID from some unknown generative distribution. And you want to use a scoring function and a search algorithm to identify the independence constraints that hold in that distribution. Now, for GES, the states that the search algorithm traverses over are equivalence classes of DAG models. So the idea here is that if you have multiple DAGs that represent the same independence constraints, we merge them together into one search state. And the operator that the search algorithm uses come in two flavors. There's the forward operators, and these correspond to single edge additions to DAGs, and the backward direction, which these operators correspond to single edge deletions from DAGs. So the greedy equivalence search works in two phases. So we start in the bottom left here with the no edge model. And then from each state, we evaluate all of the forward or green operator scores, and we just apply the best one. So we do a greedy search and run until we hit a local maximum. We call this first phase the forward equivalence search, or FES. Now, once we've reached the local maximum, we switch to the backward operators, the purple edges. And once again, we just greenly follow these operators until we hit a local maximum. So this algorithm has some large sample guarantees that, under some assumption, gives us some interesting results. The strongest assumption here is that the generative distribution itself can be represented exactly using a DAG model. So the first result is that the local maximum that we hit when we run the forward equivalence search is an IMAP of the generative structure. And by IMAP, I mean that any independence assumption that this model, a search, must hold in the generative structure. And then the second result is that the local maximum that you reach in the backward phase, that equivalence class must contain the generative structure. And so when you combine these two, it's a statement that the algorithm is kind of correct in the large sample scenario. And there's a result from UAI 2015 that if this generative distribution, if the structure is sparse, meaning that each node has maybe at most k parents, then we can prune these backward operators in dense regions of the search space, which is the branching factor is polynomial. So the previous results, we have a simple algorithm with large sample guarantees that's computationally efficient. So you might ask, well, what's more to do in this space? And the intuition about the contribution here is easier to talk about in terms of DAGs. And so the edge deletions that we're doing in the backwards phase of the search, every operator corresponds to a single edge deletion from one of the DAGs in the equivalence class. And so what's going on in the large sample limit is that if I have an edge from X to Y in a DAG, that the score of deleting that edge is going to be good or greater than 0, if and only if the Y is independent of X given all of its other parents. So what's going on is that GES is using the finite observed data to effectively be asking these independence questions from the distribution. And if it finds an independence, it's going to have a good score, and we're going to delete the edge. So the potential problem comes when we need to do high order independence tests. And by high order, I mean that the number of nodes in the conditioning set, the other parents of Y, that set grows large. And so this is particularly problematic for discrete domains, because effectively what we're doing is that when we ask is X independent of Y given the other parents, is we're asking, is it X independent of Y given all combinations of values of those other parents? So if I have 100 other parents, it's not going to be feasible. It's where we can't ever expect that we're going to get a reliable answer about this independence question from any realistically sized set of data. So the main idea of this paper is that if the generative distribution is sparse, instead of asking these high order independence questions directly, what we can do is we can ask lower order independence questions and then derive the high order independence constraints using the axioms of independence. And so for finite data, what we're going to do is that when we get to an operator that requires a high order score, we're going to replace that score with some combination of lower order scores. And the main innovation here is a case-certified delete operator. And what this corresponds to, it's a high-order delete operator that can be kind of verified to be correct in the sense that I can delete it, the independence that's required to delete it holds, but using only independence facts of order k. So the way we adjust the backward search algorithm to take advantage of this is, so we start with some IMAP of the generative distribution, and then you generate all of the backwards operators. But now we want to classify these into three buckets. So first, there's the low order deletion operators. These are the operators we can score just using kind of a small number of variables in the conditioning set. The rest of them are high order, and we test whether each one is case certified or not. If it's case certified, we're going to include it, and there's some flexibility about how we can score these with finite data, and I talked a bit about this in the paper. And so for the high order operators that are not case certified, we just ignore them. So then we greedily follow these operators until we hit a local maximum, and we look at the local maximum and we say, okay, in this maximum, does every node have at most k parents? And if the answer is yes, we're done. Otherwise, we increase k, and so we're going to do one higher order independence test as we progress through the algorithm. We go to a local maximum, ask the same question, and we continue doing this until we reach a local maximum where the parent bound is equal to this k. So the main result of the paper is that in the large sample limit, if the generative structure has no more than k parents per node, and we apply this algorithm starting from any IMAP of this generative distribution, then the algorithm is going to terminate with the right answer in at most k iterations. So I'm out of time, and I hope to see you during the poster session. Thank you.